So I'll go ahead and get started. So tonight's talk is what breaks first at scale, lessons from real world distributed systems. So we're the local San Francisco Bay Area ACM, or Association of Computing Machinery. We're a professional chapter. Our chapter has been going since 1957, holding educational talks like this. So we have a dozen or 2 dozen talks a year. We have a $20 annual membership. Upcoming talks are on our meetup site. We have about 13,000 people that have come to our talks through Meetup at one time or another. And we have at least 200 past talks of our more recent talks on our YouTube channel. We might have 1 or 2 meetings a month. We generally have 2 talk series, data science or AI, and another one that's general computing. That could be any other topic. We have an honor system jar for food backed by the pizzas. So the $20 annual fee certainly doesn't cover all the pizza for the year for a person. We have a couple of sponsors. We have a location sponsor, Valley Research Park. That's where we're located now. So they have R&D suites for rent here in Mountain View at this location. So if you're a startup, then they have office space to rent. RXM, they do cloud native AI training and consulting. So they do consulting, advising, give a training class that can be customized. Front Egg is also a sponsor. They have an out-of-the-box low-code identity platform. I'm with C-Cube, the chief of data scientists. We have a couple of products, IntelliConnect and Guardians, that are LLM-based applications. We do a lot of consulting projects as well. So these are 2 of our products that we work with for a basis for a lot of our consulting work. There'll be a chat in Zoom, or actually, on Zoom. And so one of our people will handle any questions for the remote audience. We have a call for volunteers. Start with a limited engagement. Volunteers can join us monthly. We could use some help with somebody knows WordPress. We have a .org website that could use some a little love and tender care. That's one example. Other things would be working with membership or member benefits. Audience announcements. If your company is hiring or you want to announce other local talks, events, or groups. I don't know, does anybody want to share any announcements their company's hiring or other upcoming meetups they like? Okay, we have a lot of upcoming ACM events. This is one of the most I've had on one of these slides in quite a while. So we have 1, 2, 3, 4, 5, 6. So 6 upcoming talks going through the October, November time period. So the ones in green are AI. So the next one is modern test automation and quality engineering and agile systems. Then system engineering, the role of AI and software in emissions reduction. They're all on our meetup site. I'll introduce tonight's speaker. So the topic is what breaks first at scale? Lessons from real world distributed systems by Ajinkya Kher, a software engineering manager at Meta. So as AI powered and real-time apps grow, they rely on complex event-driven infrastructure. They explore tonight's talk will explore practical lessons learned from operating large-scale messaging and distributed systems in production. Dive into the critical trade-offs between reliability, scalability, and observability. Discuss how architectural decisions compound when systems reach global scale. For some of his background, he's a formal principal engineering manager at Microsoft, has over 15 years of experience at building and leading large-scale distributed systems, real-time messaging platform that was powering Microsoft Teams and AI-powered experiences. Now at Meta, he leads teams building youth-focused experiences across Facebook and Messenger with a focus on trust and safety. So please help me give a warm welcome to tonight's speaker. Okay, go ahead and share your screen.
Thank you, Greg. All right, I should be sharing now. Are you guys able to see my screen?
Yes.
All right, do I start?
Just a minute. I'm playing with the Zoom. For some reason, it's shrinking things down quite a bit.
No worries.
Okay, that's a bit better. Okay, go ahead and continue. Thank you for your time.
All right, thanks, Greg, for the introduction. Good evening, everyone. And thank you to the San Francisco Bay ACM team for inviting me here today. And thank you all for joining. So the title of today's session deliberately asks a simple question. What breaks first at scale? Now, when we hear the word scale, oftentimes we think about capacity, be it compute capacity, database capacity, network capacity, or any capacity in general. Right? And all of that is super important. But something even more fundamental shifts as the system begins to scale. It is the assumptions with which we build the system when it was much smaller that get challenged as the system begins to scale. We will explore those assumptions today and the ways in which they get challenged. Through much of today's session, I will follow the example of a simple user action, something that a lot of us here would have done tens of thousands of times, if not more, which is that of sending a message. We'll dive into the mechanics of send message and explore how things change as we scale. I will also at time connect these mechanics to modern AI-powered applications to highlight how the core mechanics stay the same regardless of the domain in which you're operating. So quick disclaimer before we dig into all of this. The views expressed here are my own and do not represent any of my current or past employers. And the examples that I've used here are generalized to illustrate common industry patterns. All right, let's dig in. So even before we talk about architecture, I want to establish this for all of us. A user presses send on an application. At that point, they are not thinking about partitions or queues, consistency models, or any of the routing strategy. They've made one simple request, that of sending a message, and they expect a trustworthy outcome. Now, our job as system designers is not to expose the complexity of the system to our consumers, but it is to absorb all of that complexity and preserve the simplicity of the promise. That's what we are doing here. We are making a promise to the customer that we will honor the action that they've made. That is why I view customer satisfaction or user delight as the ultimate goal, and system design as a means to achieve it. It is important to ground ourselves in that because oftentimes, as we set upon building complex systems or iterating on it, we get very excited about the mechanics of it and tend to lose focus of who it is that we set out to build a system for in the first place. Uh, Making sure that the customer promise is honored is the number one priority. And everything else that we'll do is to ensure that that happens. So that's the grounding thought I want to establish for all of us before we kick in. All right, so this is the blueprint for today's session. We will explore the journey of a message, one message send operation. We'll start by defining the promise. What is that contract that we've made to the user? Then we'll explore the concepts of scalability, reliability, and observability, right? Understanding the work that goes in. Basically, you made a promise, and now can you honor that promise as the work you do behind that promise begins to grow? That, in its simplest term, is scalability. Now, can you preserve that promise when parts of your system begin to fail? That is your reliability. And then, can you actually deterministically prove that you've kept the promise? That is where your observability comes in. And then we'll connect this all together in an example that we'll walk through at a global scale. Before I begin, am I audible Is everything with the audio and video and slide sharing looking good?
You are audible, but are you moving your slides?
Am
We
I
see
moving my slides?
we see you
I
are still
am.
at first slide.
Or is it? Okay.
Are you still at first slide?
No, no, no. I am
Okay,
not.
cool. Thanks. Yeah.
What slide do you see now?
3 assumptions that break scale.
Sounds good. Yeah.
Yeah, we were seeing the
Um,
first slide until now. Now you just moved. Yeah, good. Go
got it.
ahead.
Yeah. I think I covered. If I was audible, like when I mentioned about the customer promise, I was on this slide, and then I walked through the roadmap, which was this slide. I'll just pause here for
Yeah,
a second in
we were
case.
not seeing all of them. We were seeing the
Got it.
introductory slide. Yeah.
Sounds good. So I'll just pause here for a second so that the audience catches up. And now we are at this slide, right? So yeah, we explored in the opening slide that there are assumptions that we make about a system at a smaller scale. Let's see what those assumptions could be. Right? Let's start one by one. The first one is one request is roughly equal to 1 unit of work. Now, at a smaller scale, it feels natural. At an API boundary, you make a request, you get back a response, 1 unit of work looks great. But it becomes false super quick when you deal with scale. As you fan out across recipients and devices and consumers, and a whole slew of dependencies get added on, you'll soon realize that one request is anything but 1 unit of work. We'll dig into that. That ties closely with our scalability story. And then the next one is that the failures remain local to one component. Well, you would want this to be true, but we'll see how as you scale, failures in one component have the potential to propagate to other parts of the system. And ultimately, the user views the entire journey, not component success in isolation. That is our bridge into reliability. And then the third assumption you might make is if your system is built of multiple components and each of those components is healthy, then you have a stable system. But again, remember that the user sees the entire journey. So just because you have every single component as healthy, which is super critical, it does not mean that the end outcome is essentially something that is user pleasing. The outcome could be delayed, it could be incomplete, it could be duplicated or stale. So observability goes beyond just ensuring healthy component state. So we'll dig into all of that. Now, with that, we'll formally kick off the first section, which is the user contract. Going back to our grounding example, a message sent. When can you actually say that the message is sent? So this is where we make a promise to the user. What must have completed on the backend before which our system can truthfully return that the message sending operation has succeeded? Now, this is not merely an API question. The answer here determines the architecture of the system that we'll build. We need to figure which work belongs to the critical path and which works can follow asynchronously. So the word sent in a messaging system can hide several states, right? So accepted means that the platform has taken responsibility for processing the message. Durable means that the message is stored in a permanent storage and can withstand machine restarts or failures. Available means it has propagated to wherever it needs to be propagated to, so that the intended recipients can request the message on demand. And delivered means that the message has been delivered to each and every of the intended recipient's devices, one or more devices. And seen typically requires user action beyond the platform itself. It entails that the user has actually seen the message intended for them. Now, the product should not use these words interchangeably. A collaboration product may call send operation successful after durable acceptance, but it is completely up to the scenario. It depends on the use case you're building, it depends on the product you're building. And this is where a little bit beyond system design even is the collaboration between the engineering and product teams. It is important to have a deep relationship with the product to understand what is it that you're building and what is your promise that should look like for the end user. Now, for a generic collaboration app, like we discussed, after certain validation has happened, we still need to validate that the user is authorized to send the message, is a part of the thread. And there might be a few more policy checks that happen. Once you do all of that, you persist the message in your storage. And then you also record, but that's not the end of the flow. There is some work that needs to follow. But you do not need to complete all of that, as we'll see. You record the fact that there is a work that needs to be continued. And once all of that is done, you can return success. So all of this here that you see in blue up top, that is your critical path. And then what follows in the asynchronous path, a few things are mentioned here in purple, but it's not restricted to just that. Right? You could have like derived views where each user could have like a summary of all of their threads. The user may be able to search for the messages that they or other users have sent. So you need to update the search indexes. Of course, the notification is pending. So you need to figure out the intended recipients, figure out their devices, and then deliver that message send notification over long poll, over push. So all of that work is still work that needs to be done. It is important, but that does not need to block the user action. Our promise involves the steps mentioned in blue, and it is again very critical for you to define that along with the product teams and make sure minimal things go in your critical path. Now, what we discussed for send message, basically, if I go back to the previous slide, everything you saw in purple is what we call eventually consistent. Things that are important but can be pursued as a fast follow. And one thing that often tends to happen in system design is, let's try to make this eventually consistent. I want to cover here why eventually consistent is not a universal scaling answer by contrasting it to a different domain. Consider you're using an e-commerce website and you place an order. In this case, again, ask yourself the same question. What needs to complete before which we can truthfully return back a response to the user saying that the order indeed has been placed, right? Just by clicking the button, if we return success and try to see if the item is actually in the inventory in the asynchronous path, and then also confirm if the user has a valid payment method added, it's a broken user experience. Sure, you can handle it. You place an order, you get success, yay, order booked. And then a few hours from now, you get an email or a notification saying, oops, your payment did not go through, you need to order again, or oops, the item actually isn't available. That's a broken user experience. So those things need to happen in the critical path. So what the point here is, what happens in a critical path is completely up to the domain and the use case within that domain that you're designing. And defining that accurately is half the battle won when it comes to system design. Just a quick check. Everything audible? Does audience have any questions so far? Hello, am I audible?
Yes, there is an audience question. Can you speak up loud enough? It'll carry to the microphone.
Okay, yeah, I think, sorry, maybe I missed it. But you're talking about a user sending a message. I don't understand the scenario we're using as an example. What is this message that the user is sending?
It'd be like a Facebook message.
Or Facebook message?
It could be a message on any collaboration platform.
Okay, nothing more specific than
Yeah.
that. Okay.
He understands.
Thank you.
Any other questions from the audience?
Thank you.
Okay, continue on.
All right. So what we covered so far is the critical path, right? And we briefly spoke about what things could happen in the asynchronous path. This image expands upon the same. You have kind of your derived user views, which could be updated, which is kind of just beyond the plain message send. All of the messages sent across all of the threads that the user is a part of could be summarized in a single view. That is your views. As I mentioned, your search indexes would need to be updated so that you can search for your most recent messages. You would need to handle notifications in the asynchronous path, the delivery of those notifications. And this is not a limited set. It could go beyond it. In fact, you would see as your system scales, you would get more and more subscribers and dependencies. You would have AI enrichments that need to be done. And all of these are not just dependencies that get added to the egress path. What you would see in most cases is they consume this event, they are interested in this event. And once they are done processing things on their side, they bring traffic back into our core system, right? So as you can see, it's a long tail of work that initiated with a single send message operation. So this brings to us, this introduces the concept of effective work. So all of this work that happens in the asynchronous path is the effective work. And which is why when you talk about scalable systems, request rate is a pretty weak proxy, right? Because request rate can remain flat, but the amount of work, the number of subscribers that you get, that you add in the asynchronous path actually determines the amount of work that you do. And this is a great bridge for us into scalability. So with that, we kickstart our discussion on scalability. So as what we saw so far is how accurately you need to define the promise you make to the user. Now, once you've done that, scalability in simplest terms is asking the question, can you uphold that promise as the work your system does increases? Now, going back to the example, right, what we said happens in a critical path. In a critical path, you have authorization. The user needs to be authorized to send a message. Membership, which is that the user is a part of the thread, and then some policy checks beyond that, like the user is not blocked, the user is not a bad actor, so all of that. And then you persist the message in a store. So you see all of the things here become super critical for you. They are a part of your critical path, and you cannot claim as a platform that you support 1 million requests a second if your slowest dependency, let's say in this case membership, only serves 10,000 requests a second, right? You clearly have an unspoken dependency on the network. You have a dependency on the database service provider, whichever you use. And the way you have modeled it, membership could be a different service, in which case you take a dependency on that service. So your platform, again, like can support a scale, unprecedented scale, but if membership service is not going to keep up with it, that is not of much meaning. Which is why I think another interesting point here is I covered how engineering and product team needs to work closely together. This is a classic example of how engineering teams need to work together across the org or across the company, right? It's great to have great relationships with other people, so that at any point of time, if you want to scale and you have a dependency in the critical path which needs to scale, you could make that happen. This is digressing a bit beyond system scale, but it's an interesting point I thought, which I would highlight. And again, like it is not always possible that your dependency scales at the same rate as your own service, because that dependency could be serving other use cases. They may not even consider themselves tier 0. But if you are tier 0, you need to first of all be aware of the fact that this has happened, and then figure out ways in which you can make it work even without a dependency scaling at the same rate as yours. And there are different solutions possible here. You can introduce a cache, you can eliminate unnecessary calls, you can co-locate the resources. The point is being aware of the fact that you are as slow or as fast as the slowest dependency in your critical path. That is the key here. Now again, like we said, the message can exist in various flavors. It could be a one-on-one message where the intended recipient is just one other person. It could be a group message where you have a group chat with friends and it could be fanned out to those, or it could be a large channel. Think of it like a CEO announcement on a thread. And like this is hundreds of thousands of users. And just going back to the image that we just covered, but it's not just the delivery of message to, let me go back. Oops, went all the way back. All right, this image, right? It's not just the delivery of message to those many users. Of course, that scales out with a large channel. You have to figure out the endpoints of each of the users and do the delivery to it. But then think about all of the asynchronous work that happens, right? The effective work, when you have to do those many times more now that you're dealing with a larger channel. So it all compounds. And that's what I'm calling out right here in this slide, that the subscribers accumulate in both the directions. You have the product audience, which is the recipients and the devices, but also the backend consumers. Each consumer can do something more complex. More consumers get onboarded. This is where subscriber growth comes into picture. And this is why mature systems, even though request rate stays flat, they can become expensive quickly as more and more consumers onboard. Cool, I'll take a quick pause. Any questions so far?
No questions here. Thank you.
Cool, I'll continue. So I'm going to talk a little bit about queues. Queues are one of the most interesting things in the system design. One of my most favorite component, actually. The reason is they decouple consumers and producers, right? So that each of them can scale out at their own rate. They act as a buffer to absorb short bursts, but they are not entirely magic, right? As long as the arrival rate is greater than a completion rate for short bursts, the queue can catch up. But if our arrival rate is greater than a completion rate for sustained amount of time, this will definitely lead to resource exhaustion. And then you'll have incidents bubble up in one form or the other. There's two important concepts to keep in mind, which we'll cover later here, which is the queue depth and the queue age. What does each of these things mean? queue depth is the amount of items that exist in a queue at any given point of time. Let's say there are 1,000,000 items in the queue, which means there is a backlog of 1,000,000 items to complete. Now, this could be reasonable for a larger scale system, but the important part with both depth and age is to keep a track on the delta or the drift, how much it is increasing over time. If it goes from 1 million to 2 million and it's on its upward trajectory, that's again, it ties to observability, but you need to be aware that these things are happening and be able to act upon it, because this is a sign of backlog growing. And the more interesting concept to me is queue age. There might be only 10 or 20 items in the queue, but if the item is a day old or several days old, definitely that is not a good sign. And it means the queue was not able to drain out, a particular subscriber is not able to dequeue the message. Something either in the queue itself or in the consuming subscriber has gone bust. And again, detection is the key to be able to figure these things out. Now, one other aspect of scale which is important is the fact that not all scaling cost comes from additional recipients. Oops, let me go back to this slide. So let's take an example here. Imagine two platforms which are receiving the same total number of messages. In one, the traffic is spread across millions of threads, and in others, the traffic is concentrated on a few threads. Now, in the backend, these threads are mapped to partitions. So if you have an even distribution of traffic across all partitions, then that's a healthy system. But if you have a concentrated population, going back to our example, like a large channel, and if this becomes a chatty channel, you would have one particular partition being hit at a crazy rate. Not just that it affects the request on that partition where you could see transient failures or throttles. The other threads which map to the same partition, also known as the noisy neighbor problem, could be impacted as well with this partition degrading. So we covered why request rate was a weak proxy. We also need to look at effective work. We need to look at peak rate. But also in this case, we need to look at a fourth dimension, which is the points of concentration. We need to ask ourselves the question, what is the peak traffic I expect on threads which have a single point of contention? Right? Just looking at an average peak rate is not enough as well. You need to look at peak rate per sort of dimension. In our case, with the message send example, we need to look at the peak rate per thread category. Right? And by category, you mean what is more susceptible to being concentrated in one place. And the hot partition is a classic example, but that's not the only one. Right? Let's take a different example. Let's say you have a workspace document which stores the summary of all of the threads that the user is a part of. Think of summary as something cheap, right? The last message preview and last message timestamp. Now, when you start with a small scale, you might make a reasonable choice to document all of this in a single document. The reasons are simple. It's a single point read. You can get back all of the summaries across all of your threads in a single call. It's relatively cheap. But just imagine what happens as the system keeps growing. Now this user gets added to a bunch of more threads, hundreds and thousands of more threads. And then because the user is a part of so many more threads, there is more of a probability for a message to be sent in any of these threads that the user is a part of. So now what used to exist as a low request volume on a lightweight document changes into the document being much bulkier than before and it being updated at a much higher frequency than before. And this causes some interesting problems because no matter which database provider you use, you have physical limits on the size of the document. And as you approach those limits, you will see again like transient failures like throttles or timeouts that start to creep in. So how do you solve this kind of a situation? A reasonable choice that you may make is now in the workspace document, instead of storing the summaries by themselves, you store pointers for each of the thread summaries. And the summaries themselves exist in different documents. So if a thread 1 is updated, you only need to update the thread 1's document. If thread 5 is updated, you only need to update the thread 5's document. So there is no single point of contention for all of these updates. Your workspace document still remains a point read with pointers to each of these summaries, but the summaries themselves get updated separately. So this is a great design. So should you have designed your system in this way to begin with? What do you guys think? It's a quick audience question from my side.
So there is an audience question. Could you repeat why mature systems become expensive as users scale?
Yeah, was this in reference to any specific slide or just a general question?
I think this is something you already mentioned, reference to what
Correct,
you
yeah. Because I think it's not one answer, it's multiple answers, but I think I covered some of it in the effective work. Just going back to the slide, right? Like your request rate can stay the same, but the amount of work you do in the asynchronous path can increase. That is one possible reason why systems become expensive. Um, Again, I think I covered the partition example where your request rate can stay flat, but if the messages are being sent on a bulkier thread with a single point of contention, you will see throttles. So that is a segue into reliability, really. But essentially, the effective work, right? Like as the amount of work you do per request without the request rate changing grows, that is one of the primary reasons why systems become expensive. Was there any more questions?
One question I had, Greg, the moderator.
Yeah.
When you have spikes as a problem, do you ever do anything like some kind of predictive or trend analysis? If you see spikes starting to build in certain pockets, you can handle your resource allocation a little bit differently.
Yes, that's a great question. And I think I'll cover some of it in observability, but yes, the detection to the fact that that happens is super critical, right? Like you looking at average trends won't help. You need to look at pockets of spike that come from a certain place, and then you need to be equipped with strategies to handle it, right? So again, like the spikes can be at different layers. It could be at the compute layer, could be at the database layer. For example, if you go back to this case, assuming these are all database partitions, if you see that you're getting bombarded on a single partition, you need to see what kind of traffic is being the cause here. If it's updates on a single thread, you need to look at your throttling strategy. You need to look at potentially splitting this thread across partitions. There is multiple solutions possible, but first, the primary thing is to be able to detect that something of this nature is happening. Any more questions? And first of all, did that answer your question?
Yes.
Cool, sounds good. So actually, I had a question to the audience from my side. I'm not sure if there are any responses, but I covered in the previous slide how we started with a single workspace document, kept all the thread summaries for all the threads in a single document. Then we saw with scale, it became unsustainable. Then we moved into kind of a summary per thread on its own document. So my question is, would you have rather started with this design or I just wanted to get some thoughts on what the audience feels here.
They want to respond. I do the simple one until it breaks.
Did you hear that? Somebody commented, start simple until it breaks.
Yeah, that's a great answer. I think I love the answer because it's easy enough to think that, well, now that I know it, I may have as well started this way. And maybe this is a simplistic example and it does not inherently change your cost. But there are two kinds of cost, like the cost, the dollar amount that comes from consuming more resources, and then the engineering cost of maintaining your system and your code base. So you oftentimes hear the term, let's not over-engineer it. And I completely agree with it. You should not over-engineer the implementation. But what you should absolutely over-engineer is the thought that goes into it. Right? So you can start with something as simple. And as somebody in the audience said, make it work until it breaks. Two important caveats, right? Like be aware of at what point you would need to come out of that solution and move to a different solution. So again, ties back to the point of observability. And then how do you move out? And not just how you move out, when you move out, how do you support? Because at that time you have live customers who are dependent on your service. So you need to be able to support two versions of your system. You may have dual reads happening. You may need to do like a live migration. So have the strategies for all of that prepared, but do not over-engineer the implementation itself, because how many services get to see the scale at which they might have to do something like this? And if your service actually never reaches that scale, it would have been an over-engineered redundant solution. So start small, but have the signals to be able to tell you when you need to come out of that solution and then be able to maintain that. So all of that work and thought process does go in, but you keep the implementation simple. And again, like in this case, the useful signals could be something like document size, bytes written per logical change, the amount of throttles and conflicts you see, because not oftentimes these are dealt as error code. So your quality of service can actually stay high, whereas you're seeing more throttles. And of course, the P99 latency, right? So that was a good answer. Yeah, so I said I would try to connect it with like AI powered applications. So this is a good plug into that. Think of an AI powered application that processes two requests, exactly the same request rate, which is one request. But there's a prompt A which works on a short context, does no retrieval at all, either from the internet or from your storage, invokes no tools, and in a single safety pass produces a simple output. It's a minimal amount of work that is done. Now contrast this with prompt B, right, which works with a super long, deep context. It retrieves a large amount of documents. It invokes a bunch of tools. It takes multiple passes at safety checks before it returns an output. So again, the request count is the same, but the effective work, the concept that we introduce, is a whole lot different across these prompts. Similar to send message, when you send a message on a one-on-one thread with limited number of dependencies, that's kind of identical to your prompt A. When you send a message on a large channel with growing number of dependencies which bring work back into your system, that's like your prompt B. Right? So understanding kind of what your expensive dimensions are and having a plan to bound them is the key here. And also, the point of this slide is that as you go across domains, your workload shape changes, but the core system design mechanics do not change. They kind of remain the same. All right, one note on capacity, and then I think we'll start talking about reliability next. So you often hear the term, let's throw money at the problem if you have money. It absolutely helps if your system is designed in a way where it can consume the new capacity. Again, going to the same example, it doesn't necessarily have to be a hot partition on the database, just with the way you have designed your compute. If a bunch of your workers, which can all do parallel work, are constrained on the same hot compute partition, then no matter the amount of capacity you add, it's not going to help you. But if your workers are dealing, and this is where you set up the system in a way that each worker can independently do its own work on a logical partition, then absolutely like adding more capacity can help you up to a certain extent. There is always going to be points of consolidation that need to happen. So capacity is great, but you need to set up the system in a way that can use that capacity. All right, so that concludes sort of the nature of things that happen as system begins to scale. Scalability again asks the question, can you uphold the promise as the amount of work you do starts to grow? Now reliability asks a different question, but can you uphold the promise as parts of the system begin to fail? And this is broader than just detecting and preventing outages. Right? For a send message operation, the promise includes, of course, there's a user-facing promise which we kept as simple as possible. But then in the asynchronous path, there is a commitment for availability, latency, correctness, durability, and the ability to recover accepted work. Right? So we'll take a closer look at reliability now. Digging into some of the math, right? So when you build a system and you say that it's 99% reliable, what another way to look at it is what that means is your failure budget is around 7 hours per month. So for around 7 hours a month, you can have downtime or time of unreliability. If you want to add a single trailing 9 to it and say that your system is now actually 99.9% reliable, that cuts down your capacity by just 10 times.
It's disconnected in the room. Ajinkya,
How is it?
can you
Yeah.
hear?
I can hear you. Yeah.
Can you pause for a second? It is disconnected in the room.
Sure, yeah, I'll pause.
Yeah, it is connected here.
Located in India.
Huh?
Where's this guy located?
Are the slides disconnected?
No, we are able to see the slides in the Zoom call, but in the room there is some technical glitch.
I see.
Yeah.
I'll be back. I'm back. Are we still looking at the,
You can continue.
is the connection issue resolved in the room?
Yes, yes.
Okay. So I'm not sure what was the last thing that actually I was audible in the room, correct?
Yes, you are audible. Yeah, go ahead.
Got it. Yeah. I was just curious at what point the audience kind of heard me until we disconnected, but I'll just continue from this slide. So
Yeah.
what I was saying here in this slide is, as you want to make your system reliable from 99% to 99.9%, that cuts down your failure budget by 10 times, right? At 99%, what you were saying is you have around 7 hours per month of potential failure budget. That cuts down to 44 minutes per month when you say your system is 99.9% reliable. And then if you were to add an additional extra 99.99% available would mean that you only have around 4 minutes per month of failure budget. So you can see it gets very tricky. When you begin with, it's easy to kind of make your system more reliable because you deal with it at a component level. You pick one component, you pick up a project that you deliver end to end, and then you can claim success, and then you're maybe by a trailing one or two, your reliability will go up. But beyond 99.9, it's not isolated projects that can help you get there, right? The failure budget is spread across components. So it has to be like an effort across the org. Again, this is where like engineering orgs that collaborate well together are the ones that can produce like a stable platform. If there is not a lot of coordination between your teams, this tail end problem will not be solved by one team alone. That's what I wanted to highlight here, and how tricky it is to actually create a 100% reliable system. That would be like 0 minutes of downtime forever. Now, a quick show of hands. How many in the room have clicked a submit or a refresh button on an application because it looked stuck? But I'm remote, so I cannot actually see the hands. But if somebody in the room can,
Is your volume on? Your volume on? So. Yeah, you can hear. Yeah.
So raise your hands again. I'll count and relay.
if it's not all of you, I would be surprised.
At least 10.
At least 10, yeah. I would think actually more. I would think like all of us who have done that, including myself, and it's a very human response. Quick fun fact, by the way, like the human mind perceives something as instantaneous if the response completes in what amount of time? Can anyone guess? Basically, once you've taken an action, how soon should you return a response back or a feedback from the server so that you think it is instantaneous?
1 second.
1 second.
That's too high as well. It's a good guess, but even 1 second is too high. Like based on studies, it's 100 milliseconds. Right? Anything that returns a response within 100 milliseconds is perceived as instantaneous by our brain. As soon as you cross that 100 millisecond mark, your brain already starts registering that this application is laggy. Right? That's how much we are tuned to instantaneous feedback in today's world. So it's natural that if it's taking more than 100 milliseconds, more than a second, a couple of seconds, you would hit submit again. That's a natural human reaction. We all have done it. And it's not just humans who do it. Right? Our software makes the same decisions. Clients retry, SDKs retry, services retry. All of the dependencies retry. And each retry makes sense locally, just like it did for us, because you're not sure if the request never reached the server, if the server processed it and before it could send a response, it died, or if it sent the response and the response died on the network, you have no idea. So do the clients and the SDKs and the services. They have no idea as well. So while they make a perfect sense locally, they create new traffic exactly at the moment when the system is least equipped to handle it. Right? We'll see this more closely in the upcoming slides. So now going back to the same slide that we saw earlier, that our critical path on the send message. Earlier, the focus was that you are constrained by the capacity and request rate of your slowest dependency. Now here, the point is much deeper. You take a dependency on not just the capacity, but also the organization of that dependency and its incident response. Right? For example, if you have taken a dependency on a certain cloud service provider, a certain cache or a DB, right, a certain other service in your org, how quickly are the teams responsible for those dependencies able to act upon it decides the success of your platform. Again, this is maybe not just cross-team coordination, but good coordination with your sister companies, right? With the companies that you are collaborating with is critical to ensure that you as a tier 0 service have the best response for all the dependencies that you are taking a dependency on. So this is why your critical path must be as slim as possible. You need to ask yourself the question, can the operation truthfully succeed without waiting for it? And if the answer is yes, it probably should not be in the critical path. Now let's do one more thought exercise. Right? One of the dependencies in your system slows down. As a result, the completion rate falls. Let's take an example. Right? Let's say the dependency was able to process 10,000 requests a second, and now it's only able to process 7,000 requests a second. So which means at each second, there is a deficit of 3,000 requests. So if this continues over time, all of the existing resources, right? The network, the input output ports, the memory, the CPU will be consumed by these requests which are clogged up. And there won't be any resources. There'll be resource exhaustion, basically. There won't be any resources available for new requests. So things saturate, the queues grow, and then naturally you start seeing timeouts. Now, what is it that made the incident worse? Like, was it? I have three options here. Was it the original slowdown? Was it the queuing of these requests in flight, or was it the retries? What do you guys think?
Retry, somebody said.
Yeah, I think that's the best answer, because slowdown definitely was the trigger. The queue is the accumulator, but retries absolutely are the amplifier. Right. So what happens is the dependency slows as we saw, completion rate falls, queue grows, timeouts begin, and then retries come into picture. Right. And retries are a good thing to do, but again, they need to be handled well. Right. Are you adding the retry after header? You as a service, are you honoring it? Or rather, you as a client, are you honoring the retry after header? Are you retrying only failures, only parts of the problem that are not solved? Are your retries idempotent? Right? Have you included exponential backoff and jitter? So these are all the things that you need to consider when you add retries. Blind retries, because this dependency could be processing a multi-state operation. And let's say it needs to do 10 things. 6 of those things are done and 4 failed. You need to retry only the 4 failed things and not the entire state. And also the same message could be added to the retry queue because it failed multiple times. So if a message failed 10 times, you needn't retry 10 times. It's the same message. You need to retry it once. So first you need to have the right mechanics added, and then you need to have the right observability baked in so that you can figure out the idempotency and deduplication. We'll cover more of it in observability, but this is again a classic example of retries, something that comes to a rescue, which could actually aggravate the situation if not handled correctly. So we saw how a local slowdown could become much worse. What good systems do is fourfold, right? Like they detect, they contain, they degrade gracefully, and then they recover. So detection, we covered this briefly, right? But there are telltale signs, right? Your queue depth and queue age both start going up. Your number of connections, like how many systems actually build observability into the number of input and output ports. That's a deeper level. You could argue it's a something that the cloud service provider would need to do. And I agree, in which case you need to have the right contract that they are looking at indeed all of these signals. But if they're not, if this is an in-house compute that you've spun up, you may be in charge of actually looking at the OS level metrics yourself as well. Because guess what? Like, who's building the tier 0 service? Who has the customers? It is you. So it is your responsibility to ensure either the dependencies track the right things that matter to you, or you do it yourself. Right? A number of completions will go down. So a lot of things go behind detection. The second step is containment. And once you've detected that there is a problem, before it can get widespread, contain it. Right? Isolate hot tenants. I think this was a question that I received a couple of slides back. If there is a hot partition, think about how you could split it, how you can prevent that from happening in the first place. Cap retries, like all of the things we saw in the previous slide. Add a retry after header, add a exponential back off. Right? And then the degrade is one of the critical points as well, because not everything that flows through your system is at the same priority. Going back to the messaging example, right? If you're sending a message to someone, that is a critical operation. But if it's a typing indicator, for example, that's not a critical operation. So you don't need to, when your system is running hot, try to retry a transient operation. So figure out what are the P0 events in your system, preserve the capacity at times of incident for those, and defer or drop non-P0 events, right? Where you can kind of either live with a significant amount of delay or either can live without it if the circumstances are dire, right? And then recover, which is again like partial retries, deduplication, and things that you need to do beyond at a certain time when enough damage has happened. So in an ideal world, you would never go towards the recovery path. Between the containment and graceful degradation, you would have handled it. And then the only thing you're really recovering are P1 events or P2 events. And your P0 path is clean, even at times of incident. Right? That's the clean reliability story. And I'll take a quick pause to see if there are any audience questions before commencing on observability.
No questions at this time. Thank you.
Cool. Let's continue. So as a refresher, scalability asks the question, can you uphold the promise as work grows? Reliability asks the question, can you uphold the promise as parts of system fail? Now, observability asks the question, can you actually deterministically prove that the promise was upheld? And the challenge for systems at scale is not that a signal does not exist. It does exist oftentimes. But the problem is that it may be aggregated or fragmented across teams. Without enough cross-team coordination, you wouldn't have the end-to-end observability. It could be delayed or disconnected from the user journey. Remember, user experiences the whole journey. It does not experience observability at component level. So what is important? Observability is important at 3 levels, right? The component level, the flow level, and outcome level. Let's look at what each of these mean. Right? Think of components as clients or services or queues or databases, right? Tangible components within your system. And the flow is essentially the calls and the message exchanges between your nodes or between your components rather. That is your flow. And then the end user outcome, which is what matters to the user, is the required destination state, which could be one or more nodes. If you think of your system as a graph, from graph theory, your components are nodes, and the work moves across edges, and the user's expected outcome is the destination where certain nodes need to be at a certain state. So going back to components, right? Like what are the signals that you can observe for at a component level?
What slide are you, Ajinkya?
I am at the observe the part, the flow, and the outcome slide. Is this what you see?
It just moved now. Until
Oh,
now.
is it okay? Got it. Yeah. My apologies. So yeah, this is what I was discussing. So component flow and outcome. That's the node, edge, and the destination state, which is a combination of one or more nodes. So components, like I mentioned, was like your databases, your computes, your queues, your services. So the things that help us measure component health are things like CPU, memory, instance availability, dependency errors, cache hit rate. These are all classic things that you would build as a system. Now, flow is the message exchanges between the components. And what the metrics that you would typically see associated with flow health measurement are published success, queue age, queue depth, consumer lag, like retry patterns. And outcome health is really what the user actually cares about. Right? Was the message delivered? Is the message delivery complete? Was it correctly ordered? Is it fresh? Did it complete within the promised time? So mature system needs all three. Component health is important. Flow health is important. Because component metrics are what help you locate the problem. Flow metrics reveal stalled work. But outcome metrics is what indeed answer our question, right? Going back to this slide. How can you say that the promise was upheld? It is oftentimes with the outcome metrics, which go beyond just the component and edge metrics. So I'll kind of introduce a couple of examples which show that observability is not as trivial as it looks. So let's take this example. It's a successful call. A service asks a downstream backend for a set of results. The backend returns back a response, which is contractually right. It's a valid response. It returns a 200 OK. So at any point of time here, there is no errors or exceptions that have happened. Everything looks good. Just that the response that is written by the backend is partial. It's not complete. And unless you have good detection mechanisms on the requesting service to know that it is partial, you would think everything is okay. And your system would be completely green. But guess what? The user journey, the user would have received, it could be propagated in different terms. User could have only received messages, partial messages or messages belonging to only a few threads, basically a broken user experience, right? So as we saw, this request succeeded. It was at a normal latency. There were no exceptions in the flow, but the final result is incomplete. So what are the missing signals here? The missing signals here are, did every expected part arrive? Right? Did the response indicate that more work remained? It could be in the form of a continuation signal. It could be in the form of completion markers. But there has to be some indication of the fact that the response needed to continue. And if we miss that, which is a miss on our part, system would look green, but the user experience would be broken. That's one of the examples that I've actually encountered, and these are the most trickiest to detect. Right? Now, let's take another example. Right? We saw the amount of work you do in the asynchronous path. You need to do delivery, you need to do notification. Let's say both of those succeeded. And then search is what failed. We looked into reliability, how you need to support partial retries or selective retries. Now, the basis for selective retry to work as intended is dependent on good observability and idempotent processing. If there is no way for you to detect that parts of an asynchronous flow succeeded and only certain parts failed, you would just retry the whole operation, in which you end up consuming resources that you needn't have. So observability is important to be able to support partial retries. Now let's take this entire journey, right? You send a message from a client, the service receives the request, it accepts the message, it calls the notification service. The notification service creates a push notification. Let's assume this is a push notification. The provider, which is either the Apple or the Google systems, accept it. They forward it to the device. Once they are on the device, the OS presents it. The application picks it up, and then user sees it. There is multiple things that happen through the entire journey. And let's talk about how services build kind of logging. Right? So if each of the components, and again, like these belong to different teams, different orgs, even like outside of your company, right? Like it's on the user device, OS, some of the things can be out of your control. But at each stage, typically there is an identifier which can identify uniquely the request. But if you have not carried forward the seed message, simply having one identifier across all services is not realistic. But what is realistic is to carry forward the state so that you can uniquely identify that particular identifier corresponds to a single message. Right? This is one of the trickiest examples that you'd solve. What is your reliability guarantee once a message is sent that it made all the way to the user and the user actually saw it? Because drops can happen at any rate. The service could drop. The notification service could not have generated the message. The push could have been sent. At the end of it all, it could just be like an OS setting or a user preference setting which silences the notifications because of which the user did not see. But you need to be able to tell, in that case, exactly that 1, 2, 3, 4, 5, 6, 7 were all processed successfully. 8 never happened, and then you can make those inferences. But if you don't build that observability, you do not know at which stage the message dropped. That's why kind of logging is not as simple as it looks, and it needs coordination across teams. That was a little bit on observability. Now let's take a look at a quick example of challenges that can present themselves at a global scale. Right? Let's again go back to the same example. Right? You receive a request on ingress, which is in region A, let's say. Then you need to go look up, let's say, membership check, for which you go to the thread home region, which is in region B. And then you need to check certain permissions on the user, whether the user is authorized to send a message and so on, for which you call a different service. Let's call it policy service. And for this exists in region C, right? So you can see processing a single message. And again, like regions, once all of that is done, it needs to travel all the way back from C to B to A. So it takes a global round trip, a single message, to be able to return back to the user. What we saw so far was critical path is kept as slim as possible. But even keeping it as slim as possible is not good enough if you take a hop, and this region A could be America, region B could be Europe, region C could be India. It doesn't help. It doesn't help if you have to do all of the trace, because along with it, the network, you pay for the network hop, you pay for the WAN latency. So at modest traffic, it could still be okay, but at a larger traffic, this is what would lead to timeouts. Even though you kept your critical path narrow, by not co-locating these regions in a single, co-locating these services in a single region, you created a different problem. Right? So this is where, again, like cross-team coordination is needed. Going back to this slide, you may have compute in region A, whereas the user policy service can only have compute in region C. So it may not be as simple as let's all align on region A being the home region. Right? The problems expand beyond just as simple as that. You would need to then align with the capacity team. You need to talk to the cloud service provider. Again, this is an organization problem where the cross-team coordination is super critical. But one way you could solve it is, again, assuming each of them have enough capacity in all of the regions, you can come up with the concept of a canonical home region and indicate to each other that, by the way, this is the home region, and then redirect it to that region so that the first request can take those many hops, but the next time you record it, and then everything gets processed in a single region. So this helps. And remember, at times of failover, you need capacity in other regions too. Otherwise, this will be super expensive, as well as you wouldn't have capacity to deal with failover traffic. I think that's pretty much it. As a practical design review, right? What I want you to leave with is these 7 questions. Right? If your traffic on whatever system you're building were to grow 10x tomorrow, of all the assumptions which we've covered, what assumption would fail first? It's more of a homework. You can think about it, and then what would need the more immediate attention. So that's that. I would like to close with this, right? Like, let me close by connecting back to where we started. Customer satisfaction and trust are the absolute goals. The user performed one simple action. Users do not need to understand the queues, the retry partitions, or any of the dependencies behind our system. Distributed system engineering is about absorbing all of that complexity so the user can continue trusting a simple action, even as and especially as the system grows. Ensuring that trust, despite increasing scale, is to me the art of system design. And with that, I conclude my session. If there are any more questions, I'm happy to take those.
One question from the audience. Somebody was asking if you could make the slides available. One thing we've done with past speakers is on the meetup site for your talk. At the bottom, there's a comment section that you could post a link to the PDF of your slides. Would you be willing to do that?
Absolutely, I'm happy to share these slides, yeah.
Okay, thank you. Other slides, if you want to raise your hand, I could pick on somebody and they can ask questions. Anybody want to make some guesses on the which would fail first on this 1 through 7?
Would be interesting to see which failure we had here earlier.
So maybe speak to some of these points.
So yeah, I have a question. This talk failed in the middle. Which of these is appropriate to describe that?
Well, I don't know if the speaker will be able to respond, but, so, we had a Wi-Fi problem here. During.
Yeah, I think I got the question. It's an interesting one because it's a network failure that happened. I suppose I'm not sure of exactly what the disconnection was, but potentially what could have been happening. It's more at a network level. There could have been retries attempted, and beyond the retries, the connection just decided to kill itself. If you think about it, tying back to our example, I don't know if it was connected by Bluetooth or a hard wire, but keeping that connection on was the critical path. If you saw lag in the slides load on your side, if it was pixelated, that would be like a graceful degradation. But deciding to make it kaput is actually the part that we want to avoid, right? So without knowing too many details, if I were to draw the parallels, the fact that the connection got completely disconnected is exactly the state you would want to avoid. What could be acceptable is a lag or pixelated images which recover within a acceptable time frame.
So which assumption failed first?
I would say the user promise, right? Or maybe the promise was made, the promise itself was made correctly, but it was not able to honor that promise, which meant the reliability part of it was not correctly handled.
Thank you.
Other audience questions or comments? Okay, I don't think we have other questions, but let's give a round of applause for our speaker. Thank you very much. Appreciate your time and your good content.
Thank you for having me.
Okay.
Before everyone leaves, we have this nice American Tourister backpack or shoulder bag, courtesy of Interface.ai. And it's a pretty nice one here. We're going to pull a door prize drawing ticket out of this thing. Greg, would you like to pull a ticket?
I can pull the ticket, sure.
Pull the ticket. They're all across the bottom. Ending in last two digits.
078. Anybody have 078? You're a winner.
You're a winner. And thank you very much. We very much appreciate you coming, and we appreciate those who joined tonight, and we hope to see you at many more upcoming events. Thank you so much.
Have a good night, everyone.
Thank you.
Bye-bye.
Bye.
I wanted to show that all to power of the LinkedIn page because LinkedIn page QR code so that people can follow. Yeah. But anyway, since everybody already left.
Can you just tell me please for a minute?
Yeah.
You can tell us.
Leaving, win the next one.
Okay.
I can
Yeah.
mention that.
Nobody will pay attention now.
Yeah.
I mean, no pre-occupancy, we can have.
We can have it, yeah.
Yeah.